My name is David Marx, and I'm going to talk about the phase retrieval. I'd like to point out that Fang Shi helped a lot with this to present some of his results to for the DVAC test. So I'm going to, so as AJ's already been talking about, phase retrieval is really important for the alignment and calibrations for several parts of that. So I'm going to talk, first I'm going to review a little bit of the phase retrieval method and what we predicted performance design was. Then I'm going to present the TVAC trials for phase retrieval and some of the changes we had to make as a result of TVAC. And then at just time at the end, I'll show some examples and pretty images. So for phase retrieval, the concept of phase retrieval is take intensity images at that have some focus diversity or some kind of diversity, and then numerically find the wavefront that creates these various intensity images. So we have CGI, we have pupil image and the source image, of course. And we also built in 4 defocus lenses that create defocus images of varying amounts of defocus. So defocus 1 and 2 are basically near the pupil image, and defocus 3 and 4 are near the source image. And so the idea is take these 6 images with their diversity and then find the wavefront that the unique wavefront that creates these images. Okay. So classic phase retrievals is Gershberg-Saxton iterations, which I kind of showed here. So we have in one with the pill lens, there's a wavefront incident on the lens, and then propagate through the lens makes a pupil image on the X-cam. And then also we can put in a defocus lens, and that very same wavefront incident on a defocus lens creates a defocused image. And the Gershberg-Saxton iterations are basically going back and forth, propagating back and forth in this way, and then finding a wavefront, applying the constraints at the X-cam, the intensity images, and finding the wavefront that satisfies all of that. The second approach was the parametric fitting, which is just a forward propagation. Find the wavefront, excuse me, find the wavefront that incident on the defocus lenses and the source lens gives the predicted image. And the degrees of freedom are low spatial orders such with the Zernike's. And then we have a recipe which basically combines all of this back and forth, iterating many times. And that's one slide on phase retrieval. So sources of error for phase retrieval. So phase retrieval requires a propagation model. So what I didn't say was that all this is numerical and a propagation model. So we have a model that numerically propagates all the different lenses back and forth. But it's a simple model. It's mostly paraxial. And so there are some differences between the propagation model used in the phase retrieval and truth, the actual CGI. One is bandwidth. Bandwidth. The propagation model works at a single wavelength, but where phase retrieval images are created with the band 1B, which is not single wavelength. Another difference is the doublet lenses. The doublet lenses are in the propagation model are treated as a single paraxial lens with a single focal length, but in a single plane, thin lens. But that's not quite right because doublets are not thin lenses. Integration across camera pixels, whereas so the camera pixels are finite size, but the propagation model treats them as single point. The assumptions about the common plane aren't quite right. In truth, as to where the position, basically what this is saying is that the principal plane for each lens is not exactly in the same place. And then there are knowledge errors. For example, there are lenses, each lens has an effective focal length. In our propagation model, we took the data from Optimax or the lens fabrication to determine the focal length, but that's not going to be perfect. There's going to be knowledge error there, and knowledge error regarding the propagation distance. So all these are all the differences between the propagation model using phase retrieval and truth. And so what we did in the beginning to evaluate how much that's going to affect, how much it's going to affect the phase retrieval result is we used the John Christ's CGI sim model as truth, and then played off the phase retrieval results against this truth model CGI sim, incorporating all these differences that I just described. And so these are the contributions for each one. The biggest contribution is knowledge error of the focal lengths of the 6 lenses. Okay, so that's in a nutshell how the phase retrieval works and some of the known discrepancies, sources of error that we would expect to have in TVAC, on CGI. So now I'm going to talk about TVAC itself. And the first biggest surprise was the quality of the direct image. This is a uncultured, no masks in source image in TVAC. And you can see all this, there's a lot of fixed pattern noise behind the what should be an area pattern, or the classic area pattern with the fingers from the obstruction, pupil obstruction. And on, for example, on test bed, we've always seen the source image have all the pretty airy rings and stuff, and we can get 3-4 airy rings, and that's all nice, and that contributes to the phase retrieval knowledge. But here, we just didn't have the dynamic range, and there's this fixed pattern in the background that has nothing to do with light. And so phase retrieval tries to replicate all that fixed pattern and does a terrible job. So first thing we learned in TVAC was no direct image. So now we're doing phase retrieval with 5 images instead of 6. And the next thing we do is tweak some of the parameters to see how they might improve. The phase retrieval metric is correlation between the measured images and the phase retrieval predicted images. And so the effective modifications we found that by changing the propagation distance by -1 millimeter, improved all the correlation numbers. So that's saying that the model, if we change the model by changing the propagation distance by -1 millimeter, all the phase retrieval propagation model works better. All the calculated images match the measured images better. We have a better model and therefore more trustworthy phase retrieval. So that's the second thing. And along with that was also modifying in the propagation model the airspace in the fill. Very small effect, but still there. Okay. So that was the second modification. And then the third modification is on the left here, we're flashing between, this is the measured and calculated defocus for image. And you can see that, if phase retrieval is working perfectly, these images would be identical. It would say that the propagation model from phase retrieval is perfectly predicting the measured image, and there's a difference. And so to solve that, so defocus 4 and defocus 3 were used in the parametric fitting, but not in the Gershberg-Saxton iterations. So what we did was we included in both. So by including the defocus 3 and 4 images in both the Gershberg-Saxton iterations as well as the parametric fitting on the, I guess I went forward, we get much better matching. So on the right is after this modification to the algorithm. Okay, so this defocus 4 before and after the modification. This defocus 3 before and after the modification. You can see that much better agreement. So those were the 3 modifications to the phase retrieval algorithm that we learned from TDAC. One time. Oh, okay, fine. So the last next part of a presentation is comparing metrics to the requirements. So there were three requirements: repeatability, capture range, and accuracy. So repeatability is just what it sounds like. Is if you capture phase retrieval images over and over and over again, you should get the same answer. The requirement was 15 nanometers RMS, and we did 11 repeated trials, and so repeatability was. Let's go ahead. Repeatability is defined as the RMS difference between an instance and the mean of all instances. And so the worst case, so that's this graph over here, is the what I just said, the RMS difference between each instance and the mean. The worst case was 8.9 nanometers. And that's, this is the standard deviation by pixel. And you can see that most of that just is high noisily pixel noise. If we just look at the Zernike's, the worst case was 3.2 nanometers error from the mean. And then this plot is first, the blue bars are the mean, the Zernike breakdown of the mean phase retrieval result and the standard deviation of the 11 trials from that. And the worst instance was Z4, 1.2 nanometers variation. Okay. The second requirement was capture range. So actually fairly easy to test. We had the focus control mirror, move the focus control mirror from start to finish, and show that phase retrieval still works and gets a valid result over the entire capture range. So the blue graph is measurements, phase retrieval measurements at different points along the focus control mirror course stage. The red dots are from the right axis are the RMS difference from linearity. And the focus control course stage is not perfectly linear in any case. So these results are satisfactory and improve the basic requirement was what was the requirement was 108 nanometers plus minus 108 nanometers, and we proved the last requirement was accuracy. So there's no absolute accuracy because there was no absolute truth to compare to. So what we did was a relative accuracy by moving the fine focus control mirror in small steps. That's the most of all things. That's the most knowledge we have to compare to truth. But even that was not perfect in that if we move the steps, the focus control mirror fine stage, the steps are 2.1 nanometers. There's still a 0.37 nanometer uncertainty in that motion because of creep, et cetera. But still, we can prove in a differential way phase retrieval accuracy. So the blue is moving the fine focus control mirror in these small steps and fitting to a line, and then the red dots are the variation, the nonlinearity. So the nonlinear error is maximum of 0.5 nanometers from that, which actually isn't a whole lot different from the 0.37 nanometers expected uncertainty. And then the right graph is this distance stability. So these are another set of phase retrievals under identical conditions, except for the fine focus control mirror movement and the low order measures were aside from Z4, which were stable. And then I'm going to finish with just some examples of phase retrieval in use for TVAC. This is the sequence of phase retrievals for wavefront flattening. And this is the phase retrieval results for DM registration, showing the amplitude and phase of the both actuators for DM registration, DM1 and DM2. And the last one is the back-end wavefront error, where same phase retrieval algorithm, same everything, but there's a pinhole at the focal plane mask, so that we get a measure of wavefront error of the back end. The phase retrieval result for that. And that's what I have. Thank you.
Any quick question on this?
Hey, David, so where's the 1 millimeter coming off at the final focal distance? In the phase retrieval?
Yeah. So the phase retrieval propagation model
Yeah.
is all in camera space.
Okay.
Right. So it's in that space.
Okay.
So it's the I should explain that more clearly in the beginning. All the propagation model strictly in camera space, strictly physically lens to camera. And so in the end, we're estimating amplitude and phase of the pupil image at the camera, right? And so it's that propagation distance, which ought to be the same for all the lenses,
right.
That by changing it -1 millimeter made everything work better. And I don't know if you could argue about how physical that is.
That's why I'm asking, yeah.
Because as AJ pointed out, we found that we had to take the phase retrieval result and propagate it in DM space to make that truly a pupil
Right.
image. And the field curvature and all kinds of field dependent nonsense of the pill lens. Okay.
That's gonna mess with it too.
Yeah.
Right?
So yeah, long discussion.
So that there's maybe that was just a convenient way to tweak the F number effectively of what was going on in that focal distance, make it play nice.
Right. I'm not sure about the term F number in that context, but yeah, basically it made the propagation model work better. We could have a long discussion about the physics.
Sure.
The
Fair enough.
truth. Right.
Okay, thanks.